I remember hearing someone talk about too much of a good thing. And in OSPF, we have adjacencies between two OSPF routers, and that is a good thing because they can share information and get updates. However, what happens if we have 5 or 6 or 8 or 15 routers all running OSPF that are all connected to the same Ethernet network? Does that mean they all have to form adjacencies? If that was the case, that would be a lot of unneeded overhead. So in this video, what I'd like to do is chat with you about this really cool mechanism that OSPF uses to handle adjacencies on broadcast networks. And that topic is a designated router and his good buddy, the backup designated router. Let's take a closer look. So when two routers want to form an adjacency, there's a few things. Here's router 1, here's router 2. Here's a few things that happen. They go through a state called init. Now, init's sort of like if there was a dating site and you see somebody else, you're just aware of them, that would be the init state. They can see, or one of them sees the other person's hellos, and then they start seeing each other's hellos, and they see their own router ID in the other router's hellos. And that state is called the two-way state. So they're both aware of each other. Now, at that point, if they want to continue further, there's a process called xstart and also exchange. So xstart and exchange, I kind of think of that like dating, testing the waters, talking to each other, seeing how they're doing. And then if they decide to proceed forward, there's a state of loading with OSPF. And that would be where they're learning everything about each other. They're making requests and they're getting data and updates and links data advertisements and so forth. And once it's all synchronized, that's when we have the full state. And that's really a full adjacency. And that's when we refer to these two OSPF routers as OSPF neighbors, or they have a neighbor adjacency with OSPF. And then they're going to maintain that relationship. So it's a little bit of work to get this ball rolling, and then they're going to maintain it. And it's not so bad if we have just a couple routers. But what if we have 8 routers? Let's go ahead and use these 2 and 3 and 4 and 5 and 6 and 7 and 8. If we have 8 routers and they're all connected to the same network, let's imagine right here we have a switch. And all these devices have an Ethernet interface that's connected into the same VLAN. I'll try it in here. If we have 8 devices and they all see each other's hello messages, and in OSPF they use a multicast address of 224.0.0.5, and after we introduce a DR, we'll also add in .6 to that mix. But when they start seeing each other, if they go through this whole process and we had to have full adjacencies with every device, it would look something like this. We'd have adjacencies between switch 1 and 2, and 3 and 4, and 5 and 6, and 7 and 8, and 1 and 4, and 1 and 6, and 1 and 8, and 1 and 3, and 1 and 5, and 1 and 7, and 7 and 6, and 7 and 4. Basically, it'd be a full mesh of adjacencies if we didn't have some other mechanism to control that madness. And fortunately, we do have another mechanism to control that madness, and that mechanism is referred to as a designated router. So let me go ahead and clear the screen, and let's bring up the routers again. And we'll imagine that they're all connected to the same layer 2 VLAN, the same network on a given interface. And with a switch network with Ethernet, it's going to be a broadcast network. A broadcast network simply means that if a broadcast is sent into the network, it's forwarded. So there's like serial links and other types of networks that don't support broadcasts, but Ethernet and Ethernet switches definitely support broadcast. And so from an OSPF perspective, this is a broadcast network. So the solution that OSPF came up with so that every router doesn't have to do a full adjacency with every other router is by appointing one of those routers as a designated router. And for our purposes, let's go ahead and pick R8, which will be our DR, the designated router for this OSPF network segment. And to decide the designated router, there's an election that takes place. There's a value called priority. On the interface of this router, the default priority is 1. So if the default priority is used everywhere, the tiebreaker would be the router ID. And assuming all these devices were plugged in and powered up at the same exact time, and they all had exactly the same priority of 1, the highest router ID would win as the designated router. And then all these devices would form OSPF adjacencies with the DR. So there would be a OSPF full relationship here, and here, and here, and over to 7. And over to 5 and 3 and 1. But it's not a full mesh of connections. It's not a full mesh of adjacencies. So we're reducing the number of adjacencies. Now, here's a challenge. What if there's a designated router and all the other routers establish a full OSPF adjacency with that router, and that router has a problem or goes away or is powered off? That's going to cause a disruption of service. So in addition to the designated router, we're also going to have elected a backup designated router in the event the designated router fails and is no longer available. So in this topology, let's imagine that router 7 won the role of the backup designated router. And that would also be based when all these are powered up at the same time. We'd elect the DR based on priority, and then router ID would be the tiebreaker. And so if the router IDs were all the loopbacks, and the loopbacks matched the router numbers, router 8 would win because it would have the highest loopback address of 8888. And router 7, if it had a loopback of 7777, it would be the backup because it's the next highest. And as a result of that, all the routers would also build a full adjacency to the backup. So there'd be one there, one there, one there, 1 to 5, 1 to 3, and 1 to 1. So it's still a lot of adjacencies, but it's quite a bit less than if every router was establishing a full adjacency with everyone else. So the other thing I want to cover in this overview regarding DRs, designated routers, and BDRs is, what do we call these guys? On this common network segment with all these OSPF routers connected, if this guy's the DR and this guy's the BDR, what do we call routers 1, 2, 3, 4, 5, 6 other than OSPF speakers? What we would do is we'd call them DR other, which cracks me up to this day. I mean, it feels like somebody said, okay, what do we call these guys? They're not a DR, they're something else, or let's just use the term DR other. And what I think of is think druther. I'd rather not be a DR, I'd rather not be a BDR. So all of these devices, 1, 2, 3, 4, 5, and 6, would be, if we looked at their interface that's connected to this common network segment, it would show a status of druther, meaning I'm not the DR and I'm not the BDR. And if we did a show IP OSPF neighbor on these routers, like router 2, it would show that it has a full adjacency with router 8, the DR, and it would also show that it has a full adjacency with router 7, the BDR, and because we're on this common segment and R2 can see all the hello messages from everybody else, it would show something like this, two-way druther as its relationship with R1, with R4, with R3, R5, and R6. Because the two-way state simply means that we can see in those devices hello messages, which are sent on multicast, we can see our own router ID, so we know about each other, but we do not have a full adjacency, and so those will show up as two-way druther. Now, let me share with you why this is important, because when OSPF is implemented and working, it's great, no problem, but if it's not working or if it's having a problem, we should be comfortable in the logic behind it. And what we'll do in the next video is we'll do a lab so that we can do the commands of show IP OSPF interface brief. We can take a look at the roles and statuses. We can do a show IP OSPF neighbor. We can see what the neighbor adjacencies look like, whether they're full or two-way, and whether that adjacency is with a designated router or a BDR, or it's a two-way state simply with one of the other devices on that common segment. So the best way of getting that experience and that exposure is hands-on. So that's what you and I are going to do in the very next video. So I'll see you there in just a moment. Meanwhile, I hope this has been informative for you, and I'd like to thank you for viewing.